Okay, let's dive in. We're tackling something pretty fundamental today in AI, specifically how these huge transformer models, the brains behind ChatGPT, Claude, even AlphaFold, how they actually learn what matters in a sequence of text. We know attention is the magic word, but how the numbers representing words, the token embeddings, and the attention parts themselves learn to spot and focus on important information during training. That's felt a bit mysterious. So our mission today is to unpack that. We're looking at sources centered on a really interesting new academic paper that gives some solid theoretical grounding. It's not just saying what attention does, but digging into how training shapes these embeddings to capture importance and make selections.
That's spot on. We've seen these attention models work incredibly well in practice for years now, state-of-the-art stuff. But the why does the training process, gradient descent usually, make the embeddings behave like this? Why does attention learn to focus correctly? The rigorous math behind it has lagged behind the practical results. This paper tries to build that theoretical bridge. The main source is Attention with Trained Embeddings Provably Selects Important Tokens. The authors are Diyuan, Aleksandr, Shevchenko, Samet, Oymak, and Marco Mondelli, folks from ISTA, ETH Zurich, University of Michigan. Serious researchers digging into the theory.
Right. And with theory like this, you often can't tackle the full complexity of something like GPT-4 directly. They usually simplify things to make proofs possible, right? So what was the model set up here?
Exactly, you need a controlled environment. They used a simplified model, just one layer of softmax attention, paired with a straightforward linear head for classification. Specifically, it's set up for binary classification, deciding between two outcomes based on the input sequence. Think positive and negative sentiment, maybe.
Okay, so one layer, binary task. What are the moving parts?
You've got your input tokens, each with its own embedding vector. We can think of these collectively as a matrix, $. Then there's a special token, often called the KSUF token, which also has its own tradable embedding vector. Let's call it $. This $. is really key for the attention process in their setup. And finally, there's a fixed output vector, which is part of that linear classification head at the end.
Got it. So how does the classification actually happen? How does attention work in this simplified version?
Well, the model's final output depends on a weighted sum of all the token embeddings. And the weights, this is the attention part, come from applying the softmax function to the dot products. Specifically, the dot product of the SACI embedding, $, with each individual token embedding in $.
Ah, so the similarity between the ACE and state and each token determines its weight?
Precisely. Higher dot product means potentially more attention. Then this weighted sum of embeddings is combined with the output vector $, to get the final score. And the trainable bits, the token embeddings $, and that crucial ASA embedding $, are learned using standard logistic loss and gradient descent, or technically gradient flow for their proofs, which is like a continuous version.
Okay, simplified model, standard training. Now, you hinted earlier that something quite significant happens really early in training, like unbelievably early, one step.
Yeah, that was one of the first big surprises in the paper. It kind of goes against the intuition that learning takes time, takes many updates. Their Lemma 4.1 proves, mathematically, that after just one single step of gradient training with this setup, the token embeddings X already start reflecting a measure of how important each token is for the classification task.
One step. How? What kind of importance are we talking about here? Is it like semantic meaning?
Not semantic meaning in a deep sense, no. It's more statistical. The proof shows the update pushes each token embedding to align with that output vector $, and the amount it pushes depends on something they call the average signed frequency, or alpha $, for that token.
Average sign frequency. Okay, break that down.
Sure, for any given token, say the word great, you count how many times it shows up in positive examples, then you subtract the number of times it shows up in negative examples, and finally you divide that difference by the total number of tokens in the whole dataset.
Ah, okay. So it's not just frequency, but frequency biased by the label. If a word appears way more in positive sequences, it gets a high positive alpha $.
Exactly. And if it's mostly in negative ones, a negative alpha $. If it's balanced or rare, alphas is near zero, meaning it's not very predictive just based on this simple count.
The Lemma 4.1 connects this alpha $, to the first training step.
Yes. It shows the update to a token's embedding includes a term that's basically alpha scholar times the output vector. Remember, the $$ points towards the classification goal. So the embedding gets pulled towards dollar strongly if its dollar is large, positive or negative, and barely at all if alpha's dollar is near zero. It's a really neat result showing this basic statistical importance gets baked into the embeddings almost immediately.
That is fascinating. The raw embeddings start capturing this signal from step one. Okay, so EX dollar gets this initial importance imprint. But attention itself, the actual selection of which tokens to focus on, involves the Aquel token $T, right? What happens with $T as training goes on?
Good question. That's the next big piece of their analysis. They investigate the implicit bias of training $Kudge using gradient flow after that initial step. This is where the model learns which tokens to actually pay attention to, leveraging the important signal that's now starting to appear in the EX dollar embeddings.
And this leads to another key result.
Yes, theorem 4.3. Now, to make the math practical here, they introduce a simplification called assumption 1.
Assumptions in theory papers, what does this one assume?
It assumes that every sequence in the training data has exactly one token that is completely positive, appears only in positive sequences, or completely negative, appears only in negative sequences, and all other tokens are irrelevant, have alphas equals $0.
Okay, that's definitely a simplification of real text, but I see how it isolates the effect. What does theorem 4.3 prove under this assumption?
It proves several interesting things about how dollar behaves. First, via lemma C.1, the length or norm of the PLR vector grows infinitely large during training.
Goes to infinity. Why is that significant?
They interpret it as the model becoming increasingly confident in its selection strategy over time. The direction matters more than the magnitude eventually. And speaking of direction, theorem 4.3 part 1, building on another lemma, shows that if $P direction settles down, it must point in a way that effectively selects all those completely positive and completely negative tokens, the ones with the strong, non-zero alphas dollar.
So it learns to pick out the important ones defined by assumption 1. Makes sense.
But here's the really crucial part, the core theoretical insight, I think. Theorem 4.3 part 2 doesn't just say it selects them, it characterizes the direction $P converges to, approves this direction is the max margin direction for separating those important tokens from the irrelevant ones.
Max margin, like in SVMs. Trying to find the biggest gap. How does that apply to selecting tokens with $P?
It's conceptually similar. Here, max margin means $P learns a direction in the embedding space. When you project all the token embeddings onto this direction, which is what the dot product $exp rangle dollar, that the important tokens, the completely positive and negative ones, get pushed as far away as possible from the irrelevant tokens, those with alphas equals $0. Think of it like drawing a line, or hyperplane, dictated by $T. The model pushes the important token embeddings far out on one side of a threshold determined by the Softmax, and keeps the irrelevant ones close to or on the other side, maximizing the separation. This leads to very high attention weights for important tokens and very low weights for irrelevant ones.
Okay, maximizing the separation. And you said proving this is the max margin direction is the big innovation. Why is that distinction important compared to, say, just showing it finds some good separation?
Right, it's a stronger theoretical claim. Some prior work might show convergence to a solution, maybe one that's locally optimal. But this paper, under Assumption 1, characterizes all possible convergence directions of $P as being equivalent to the globally optimal max margin solution for this specific token selection task. It tells us something precise about the kind of solution that gradient descent implicitly prefers in this attention setup. It's not just finding a way, it's finding the geometrically optimal way to separate based on the learned embeddings. That's a much deeper statement about the learning dynamics.
That's a significant theoretical step, showing it converges to this optimal geometric boundary. So it selects the important tokens, does it definitely ignore the irrelevant ones. Could $P accidentally highlight some alphas eco-dollar tokens?
They address that too. Lemma 4.4 provides a proof that the final dollar direction cannot select all tokens in the vocabulary. Since theorem 4.3 says it does select all the important ones, under assumption 1, this implies it must not be selecting at least some, presumably the irrelevant ones.
So it has to leave some tokens out.
Yeah. And lemma 4.5 goes further. It gives a specific condition related to the margin sizes. If the max margin solution that selects only the important tokens has a strictly bigger margin than any solution that might try to include some irrelevant tokens, then the training dynamics guarantee convergence to selecting only the important ones.
And is that condition likely to hold?
The authors suggest it probably holds when the important tokens, both positive and negative, have roughly similar statistical strength, similar absolute values of alphas dollar. So for many reasonable datasets, the theory predicts clean selection of only the relevant tokens.
Okay, the theory sounds compelling. Embeddings grab statistical importance fast. Then this S2 token learns this optimal max margin way to select them. How did this hold up when they ran actual experiments? Did the theory match reality?
They did run numerical tests, which is crucial. They used synthetic data that fit their assumptions, but also, importantly, they tested on real, messy datasets like IMDB movie reviews and Yelp reviews. They trained their models and then looked at the learned embeddings and attention.
And what did the plots show? Did they see the alpha dollar effect and the max margin selection?
Yes, quite clearly, qualitatively. If you look at the figures 1, 2, and 3, there are usually two types of plots per figure. The plots on the right typically show the dot product between the token embeddings and the output vector, langle-EX v rangle-dollar, versus some measure of token importance, like that alpha-dollar proxy. These consistently show a nice linear relationship. Tokens, strongly positive. High dot product, strongly negative. Low dot product. It's exactly what Lemma 4.1 predicts about embeddings capturing importance.
Okay, so the first part, the embedding importance, shows up nicely in experience. What about the selection part, the langle-EX p rangle dot product?
That's shown in the left-hand plots. They plot Langle EE P Rangle against the same importance measure. And here you see this really characteristic V shape or sometimes a U shape.
A V shape. What does that mean?
It means the dot product Langle EX P Rangle, which determines the attention weight, is high for tokens with large importance, whether positive or negative, the extremes of the V, but it's low for tokens with importance near zero, the bottom point of the V.
So it gives high values to things that are strongly predictive regardless of which way they predict. That sounds exactly like selecting based on magnitude of importance.
Precisely. It's the visual signature of that max margin selection. It's selecting the statistically important tokens, high alpha's dollar, and deselecting the irrelevant ones, alpha approx $0, just as theorem 4.3 described. And what's really encouraging is that these patterns, the linear relationship for Langle EX V rangle and the V shape for Langle EX P rangle, don't just appear in the clean synthetic data. They show up clearly on IMDB and Yelp, and even in Figure 1, which shows results for a slightly more complex two-layer model.
So the core ideas seem to generalize beyond the simplest theoretical setup.
It strongly suggests these mechanisms' early statistical importance capture and max margin selection by the ASLAs-like dynamics might be pretty fundamental, even if proving it for deeper models is way harder.
That's very convincing when the experiments back up the theory like that. So given this success, what are the main caveats or limitations here? What doesn't this theory explain yet?
Well, a key limitation, which the authors acknowledge, is that the importance measure, alpha dollar, is based on simple frequency and correlation with the label. First order stats, basically. It explains how attention might learn to find keywords like brilliant or awful, but real language is much richer, right? It has grammar, word order matters, negation flips meaning, complex relationships between tokens. This theory doesn't really capture how attention learns that kind of deeper causal or sequential structure.
Right, it's focused on individual token statistics.
Exactly. And the rigorous proofs are for that specific one-layer model under assumption 1. Extending the proofs to multi-layer, multi-head attention, like in real transformers, is the next big challenge.
So where does that leave us? What's the future direction?
Well, the authors propose an interesting idea. Maybe in deep multi-head models, different parts specialize. Perhaps early layers learn some of that sequential causal structure. People talk about induction heads doing things like copying patterns. And then later, layers might rely more on the kind of statistical importance, like the alphas mechanism proven here, to make the final classification or decision. So this paper provides a solid theoretical foundation for understanding that second part, the learning and selection based on empirical statistics. The next step is figuring out how that combines with learning the structural aspects of language.
This has been incredibly insightful, really peeling back a layer on how attention works. So a quick recap. This paper gives us strong theoretical evidence that token embeddings learn statistical importance really fast, like step 1 fast. And then the Cs token, through its training dynamics, learns to perform an optimal max margin selection of those important tokens, separating them geometrically from irrelevant ones. And experiments back this up qualitatively even in more complex settings.
That's a great summary. The core innovations are really proving how that initial statistical importance gets encoded, and crucially, characterizing the specific nature of the selection as being this max margin process. It's a more precise guarantee than just saying it learns to select useful tokens.
It makes you think, though, the theory explains selection based on frequency and simple correlation really well. But when we interact with something like ChatGPT, it feels like it understands way more than just which words appear often with positive or negative contexts.
Absolutely, and that's the frontier, isn't it? This work gives us a rigorous handle on the statistical learning part. The huge open question now is How do we theoretically connect this understanding of learned statistical importance with the learning of complex, sequential, maybe even causal relationships within language? How do these mechanisms work together in deep models? Answering that will give us much closer to a complete theory of how attention truly understands. Definitely a deep dive for the future.